Okay, we are recording. The lecture will start in about 5 minutes. It's the only way I can remember to actually record is start recording as soon as I turn the Zoom on. Good morning. Okay, we'll finish up chapter 6 today. It's a short chapter, so it's about, well, really Ohm's law is kind of the topic of the entire chapter, and we'll start chapter 7 then on Friday, which is where we'll first start looking at magnetic forces. and magnetic field. I want to talk about calculation of conductance in a coaxial cable today, or conductance in general. It's actually directly related to conductivity, and we looked at calculation of resistance last time in a conductor, and then we'll also talk about power. So see how you can calculate power actually from the fields and how that's related to the traditional power formula that you use in circuits. And then I'll work through an example of actually calculating resistance. It's similar to one of the homework problems that was assigned. So what we're going to look at is calculating the conductance of a coax. So it's got an inner conductor and an outer conductor. And so we're going to do this one a little bit differently, actually. So one technique would be to apply the voltage, and like similar to what we did with resistance last time, is apply the voltage, calculate the electric field, integrate the electric field to get the voltage. But we show a different approach this time, where we'll apply a current to an open terminated coax. So the only current flow here would actually be between the inner conductor and the outer conductor. And typically this would be really, really small, because the conductance is so low, or the resistivity is so high in the spacer material. So again, it's convenient here to actually use cylindrical coordinates. So I'm going to lay the z-axis on a side like that, and the the radius of the inner conductor is A, and the radius of the outer conductor is B. And we'll use the left end here as our z = 0 coordinate. So this is our rho axis, and we'll calculate the conductance here over a length L of the coaxial cable. Get much better drawing these things. There will be, a current density present due to the current flowing between the inner conductor and the outer conductor. And you wouldn't have to do this in terms of conductance. We could calculate the resistance. Conductance is just the reciprocal of resistance. So you would never have to use conductance in any circuits problem. It's just more convenient in problems involving parallel devices, because the conductances just add and the resistances are the reciprocal of the sum of the reciprocals. But then the other thing in our transmission line equations, way back in chapter 2, the telegrapher's equation, the model we used for the coax actually had a conductance between the inner and outer layers, and the equations are just easier to write in terms of that conductance parameter G. We used R to model the resistance of the conductors themselves, the inner and outer conductor, and work through a problem where we actually calculate that resistance. But now we're talking about this resistance between the inner conductor and the outer conductor. That's filled with this material, dielectric material that has very low conductivity. Ideally, there wouldn't be any current flow between the inner and outer conductor. But the transmission line model includes a conductance per length term G prime. Okay. So this is the conductance of the dielectric material or the spacer material that exists between the inner conductor and the outer conductor. So a couple of weeks ago, we actually calculated the capacitance per unit length of the line. Last time, we actually calculated the resistance of the conductors per unit length. And today, we'll calculate the conductance between the two conductors. There was one other parameter that was in that transmission line model. It was inductance per unit length, L prime. We'll be doing that over the next couple of weeks as we talk about magnetic forces and how that's related to inductance. And we'll be able to calculate the inductance of a conductor just like we calculated the capacitance between two conductors. So I'm going to make an argument based on symmetry here that the current density through a virtual cylinder of radius rho is just uniform. It's the current divided by the surface area of this virtual surface. So if you can imagine, I'll show it kind of in a dashed line here, this virtual surface here surrounding my inner conductor. And I'm interested in the current density there. What the assumption, it seems like a reasonable assumption, is that the current density is current per area, is that's uniform along the entire length of the conductor. Okay, that would be the case, if there is no change in voltage along the length of the conductor. The voltage here is the same as it is at the right endpoint, and that's true then for a perfect conductor. So I'm making that assumption. It seems like a reasonable assumption here that will model that inner and outer conductor as perfect conductors. This is just saying that J is directed outward and has equal magnitude, at all angles around the inner conductor. Now, that virtual surface, as its area gets larger, then the current density is going to go down. I is constant, but the current density is this total current I divided by the surface area. So that's equal to 2 pi rho L. So what I'm actually calling now, this distance here is, I could call it rho prime, because I'm using rho as that axis, but I think we can call it rho and be clear about what we mean. It's the distance to this virtual surface. Now, an important relationship we had last time is this Ohm's law relationship. It's kind of fundamental here. It allows us, if we know the E field in a conductor, we can find the current density. If we know the current density, we can find the E field. It's as fundamental as Ohm's law. It is Ohm's law for electromagnetics, or the point form of Ohm's law. So the E field would be I divided by sigma s 2 pi rho L. So now I want to find the voltage between the two conductors. And I can get that by just integrating. And here, we've got the current directed, the voltage would be positive from the outer conductor to the inner conductor. So I'm going to calculate that positive voltage. So it's just E dot dL. Again, the assumption here is that the voltage is the same all along the inner conductor and then also all along the outer conductor. Those voltages are different because the entire voltage difference is due to the conductivity of the spacer material. Or going to integrate again from the outer conductor at radius B to the inner conductor at A, and then substitute in my formula for my E field, rho S 2 pi rho L. And then my length element here is just along a radial line. I'm going to take the simplest path. And it doesn't matter what path you take, but I'll take the simplest path just along a radial line. So this integral, most of this is a constant. I've got rho hat dot rho hat, which is 1. And pull out most of this stuff minus I over rho S 2 pi L. And I'm integrating just 1 over rho. So that's the natural log of rho. And evaluating that at B and A. So that becomes I over rho S 2 pi L. And then it would be the natural log of A minus the natural log of B. I'm going to get rid of the minus sign by incorporating that. It would be natural log of B minus the natural log of A. But the difference of natural logs is just the ratio of the two arguments. So it becomes natural log of B over A. And then finally, now I got rid of the negative because the natural log of A minus B, and then so I incorporated the minus sign as natural log of B minus A then, which is the same as natural log of B over A. For conductance, V is equal to IR, or I is equal to 1 over RV, or I is equal to G times V. We have G is equal to I over V. And so take my expression for V here, take its reciprocal, divide that into I. The I's will cancel out because it's present in both terms. And I get 2 pi sigma S, which is the conductivity of the spacer material, natural log of B over A. And squeeze this in here. The conductance per unit length is G prime is equal to G over L. It's 2 pi sigma S over natural log of B over A. And if you look back in chapter 3 of your textbook, we covered this section on coaxial cable, and we had these formulas for inductance, L prime, capacitance, C prime, conductance, G prime, and then the resistance, R prime. Okay. And then this is the formula that we used back in chapter 3. Okay. So it's taken us 3 more chapters and an understanding of electric fields and current density in order to get that, to derive that conductance equation. Okay. So previously, when we talked about energy, we talked about moving a charge relative to the field and then the work that was done against the field. Now we want to talk about the electrical energy that is exerted or expended by the field and creating this current. So the power expended by a field E in moving charge in a conductor is, and he has a proof of this in the book. I'm not going to go through the proof, but if you're, it might make some sense, you know, at some level. If you remember from circuits, we talked about power as being current times voltage. Well, here we've got, you know, the electric field, which is voltage per distance, and then the current density, which is current per area. So this product would be voltage times current per cubic meter, or power per cubic meter. So this is a volume integral. Okay. So it makes sense, at least from a unit standpoint. You know, the physics, you can look in the textbook where it goes back to actually, you know, Coulomb's law for the force exerted on a charge due to the electric field, and derives this equation. But from a unit standpoint, it makes sense. The electric field times the current density has units of watts per cubic meter. We integrate over volume, and we would get watts. This is called Joule's law. The power here, the electrical power that is, we usually often say it's lost. Of course, power is not lost. Energy is converted from one form to another. In conductors like this, the electrical power is converted to heat. Okay. So, you know, resistors get hot. Okay. And this is the basic principle, like on how electric heaters would work. Okay. So where V is the volume of the conductor. So you have to integrate over the whole conductor. Now we can simplify this a little bit. We know that J is equal to the conductivity times E. So this becomes E dot sigma E dV, or it's not a vector, P is equal to E dot E is the magnitude of E squared. So we can write the power like that. This would be kind of analogous to power being V squared over R, right? So conductance is 1 over resistivity. So conductance times E squared again is kind of like V squared divided by R. The power is proportional to the conductivity. The higher the conductivity, the greater the power that's absorbed. It's also proportional to the square of the intensity of the E field. Okay. Now, the power dissipated in a perfect conductor, a perfect electrical conductor, is 0, because remember, in a perfect electrical conductor, our E field is 0. Let's see if we can put this in a more familiar form. For a conductor aligned along the z-axis as shown. So I'm going to draw another cylinder, but I'm going to orient it differently. Say it has a length L again. This is a solid cylinder. It has a cross-sectional area of A. This is the z-axis. This is rho. And it has a conductivity of sigma. I have some applied voltage V across it. And now, again, our current density points in the same direction as traditional current. So J would be downward. And then in here, as long as the frequency is low enough, J would be uniform everywhere in the conductor. Well, actually, we could start with J, but I'll actually start with the E field. The E field is going to be pointing in the same direction as J, and J is sigma times E. So I'm going to actually start here now with the electric field. Instead of assuming J that was constant like I did previously, we'll just assume that, start with the assumption that the E field is constant along the conductor, and then P is equal to the volume interval just from the previous equation of the magnitude of the E field. Now the magnitude, take the absolute value, the negative sign goes away. Power is always positive. So EZ squared times sigma, integrating over the volume. But here are sigma and EZ are constant throughout the volume. So that will just become sigma times EZ squared times V, which is the volume of the cylinder is just its length times its cross-sectional area, L times A. I'm going to write this as sigma EZ A times EZ L. But sigma EZ is JZ A. I can rewrite it like that. Or finally, I get JZA, the current density times the cross-sectional area is current. So JZ times the cross-sectional area would actually be the current flowing through the conductor. And then EZL is our electric field intensity times the length, that's voltage. So we get here for this conductor that this electromagnetic formula for power reduces to the form we're familiar with from circuits, just I times C. And remember, this was the formula we had for DC circuits. It's valid for a time when the currents and voltage are time varying as well, but then it's the instantaneous power is equal to the instantaneous current times the instantaneous voltage. And we have to time average to get the average power. Okay, wanted to work through an example from one of the problems, 6.4-2. I think this is very similar to 6.4-1 that I signed last time. They want us to come up with the resistance of coaxial cable. Now, here I'm just going to draw, kind of an end view of the cross section of the coaxial cable. So this is the spacer material. And the radius of the inner conductor is A. And in the problem statement, they give us the diameter. So A is actually the diameter, 0.0584 centimeters divided by 2. And they give us the conductivity of the material. It's 2.28 times 10 to the 7th Siemens per meter. And then for some reason, instead of just giving us the inner and outer diameter of the outer coax, they give it to us like this. They give us the mean diameter. So the mean radius is the mean diameter divided by 2. So I call that B bar. So it's not an electromagnetic field, but the bar in probability statistics indicates an average value. So, and then they give us this additional information about the thickness. The thickness is 5% of the mean radius, 0.05 times B. So we could get a number for T. Okay. Now, they ask us to find the resistance per unit length here, the R prime parameter. Okay, so I don't think, I think I said earlier we did this, but I guess we didn't. I was thinking of this example problem. We set up this problem last time. It's, if you remember the formula for resistance, it's the length of the conductor divided by sigma times A. So as it gets longer, the resistance goes up, but as the conductivity goes up, the resistance goes down, and as the cross-sectional area goes up. So here we actually have two conductors, and they would actually be in series, and then the coax, the current flows along the inner conductor and then back along the outer conductor to whatever the load is. So we want to actually add these two resistors together so that they're not really in parallel. It would be R inner to the load, and then R outer is our model. So the resistance of our coax per unit length is actually the sum of those two resistances. They're not, may look like they're in parallel, but they're actually not. The inner one is really simple. Starting with our basic formula, L is the resistance is the length divided by sigma A. Then R prime inner is just 1 over sigma A. It's resistance divided by the length. And for the inner conductor, it's a perfect circle. So that cross-sectional area is just pi times A squared. So at this point, we've got all the information we need to calculate this resistance. And it's 163.7 milliohms per meter is R prime. Now the outer one's a little trickier. We just need the formula's essentially the same. The length is going to be the same. I'm still going to use A for, maybe I should use AI here. So it's clear that I'm talking about an AO for this. It's, how would you calculate the cross-sectional area of that outer conductor? Pi times the radius to the outer radius squared minus pi times the inner radius squared. So that, again, R prime outer is 1 over sigma A0 where A is pi times B bar plus the thickness divided by 2, right? Here's B. So the outer radius is B plus T over 2 minus B bar minus the thickness over 2 squared. So that would be A0. Now at this point, we've got numbers for all of this, so you could plug in directly and get this. You can simplify this a little bit though. If you go ahead and square these terms, you'll get a B bar squared here minus a B bar squared. And the last terms cancel as well. What you get is just quite simply pi times 2 times T times B. And in this case, T is 0.05 B bar. So 2 times that is going to be 0.1 B bar squared. And so now you can finally calculate the R outer prime. It's 1 over sigma pi 0.1 B bar squared. And that's 40.57 milliohms per meter. So there's greater resistivity in the inner conductor than the outer conductor. I mean, and if you look at coax, the outer conductor is usually pretty thin, but because it has a greater radius, it has the larger cross-sectional area. So finally, R prime is the sum of these. And that turns out to be 204.3 milliohms per meter, which I think if you look up the resistivity of RG59, I think these numbers are consistent with RG59 coaxial cable, that this result is pretty similar to what you'll find in the tables. 0.2 ohms per meter. Any questions about that? All right, that actually finishes up chapter 6. So I'm going to stop there, let you go. And then I don't have your exams graded. I started grading them, so I should get them back to you on Friday. So